Computer, here we go. Ka-ching.
Okay, awesome. Excellent, that's one less thing I have to worry about. Awesome.
Splendid.
So good morning, everybody, and welcome to another webinar series. And hopefully you can see the screen there. Excellent, thanks Greg for the confirmation. So this is a slightly different format, and it'll be really interesting to get as many people involved as possible. We thought we'd, rather than going through a boring presentation and just listening to slides, we'd do it in a sort of question and answer scenario, recognizing that it normally takes a while for people to warm up. I've prepared some slides and some questions for Greg, and if I only do 2 of the questions because everybody else asks questions, then that's absolutely perfect. It's a perfect opportunity to grill Greg, as without doubt, I don't think there's anybody else within the company who knows it inside out like he does. So thank you, Greg, for staying up into your evening to do this. So welcome.
Grill Greg probably sounds like a better title than Ping the President.
Well, I think people were worried Donald Trump would turn up, so that's another issue. So feel free to ask questions. We've got Eduardo, and I think Dan was also planning on joining, but Eduardo is certainly there and can answer as we go, as I will try and ask and answer questions through the chat box. But it's meant for everybody to have the opportunity to talk, so by all means interrupt and ask Greg as we go. I have some slides prepared. I'll try and find the right one if it's appropriate. If not, we'll just look at Greg while he answers, which will be awesome. So let's give it a go. So Greg, the RBR has been operating now for close up to 50 years. We're heading into 50th year in a couple of years' time. Do you want to just give a quick introduction to yourself?
Yeah, sure. So I was born in the year that RBR started. And so RBR is 47, and so am I. Most people who've been around RBR for a while know that what RBR stands for, but some don't. So it stands for Richard Branker Research, because Richard was an English engineer who'd moved to Canada who started the company. And in its early days, when I was still in nappies or diapers, as you prefer, RBR was doing electronics consultancy for the federal government in Canada, lots of interesting one-off projects. However, in the late 90s, when Frank Johnson took over, we didn't change the name of the company to FJR, we left it at RBR. But Frank, who's my father, and my sister, Kara, ran the company together for about 12 years until I came back from France, and I'd been kind of in the academic sphere doing instrumentation for lots of different areas, X-ray, imaging, and various bits and pieces. And so I came back to run the R&D group at RBR. We were about 20, 25 people at that time in some residential houses still. It was quite amazing that we managed to do that for so many years. And shortly thereafter, we moved out to what was really our first professional office, which is, if those of you who have been watching our address recently have noticed that our address has changed. We'll have some exciting pictures to show you in the next month or so of the new office, as we've just moved to increase the amount of space we can use. So yeah, I started off running R&D. I've got an electrical engineering background, and I've been chief cook and bottle washer for the last few years.
Awesome. So I'm going to ask you, because we always ask our guests about a fun fact, and do you have a fun fact which is not the same as the last one?
Rats. Rats.
I reckon you should tell people what you're actually converting at the moment. I think that's awesome.
There we go. Okay, yes. So as any of you who are involved in any kind of commercial activity which involves traveling, the last 6 months have been tremendously boring as you haven't been able to travel anywhere. And that's the same for me. And most of the company now wishes greatly that the COVID restrictions were lifted so that I could travel and they could get me out of the company. I decided to take matters into my own hands about 3 months ago, and I bought a white van. So that officially in English terminology makes me a white van man. It's a panel van. It's designed for carrying about a ton in 1,000 kilograms of bricks or plumbing supplies or electrician's tools or whatever. But I'm converting it into a camping van. So I'll look like I'm a commercial plumber, and I still have some of the stickers on the outside. In fact, it was a concrete forming company that owned it before me. But I've learned the joys of cutting holes in sheet metal. I never thought it would be fun to cut a hole in a vehicle before, and it took me about 3 hours before I got the guts to cut the first one. But once you've done one, then you feel like cutting holes in all the panels. And I've cut 3 holes in my vehicle so far. It's not going to stop.
It will be very interesting to see how the next generation of loggers turn out, whether they use the same tooling, but hopefully not. Excellent, thanks, Greg. So the RBR range of instruments can be used for a whole range of applications. There's a few images I've got here of this is a mixing project study in Vietnam. This is a tidal study in a bay, and I've done something similar in Port Kembla. Is some scientists deploying it's not a thermistor array, but it's a range of instruments, depth loggers, temperature loggers, and TD loggers, I believe, off the side of a vessel attached to ropes. And then here we've got some citizen scientists using the CTD with the Wi-Fi connected to a iPad device, and we attach our loggers to vehicles, and we've got some beautiful ones. In fact, there's a Nortec logger involved in that photo, so Yaron will be really pleased because I can see he's online. And the British Antarctic Survey here have got loggers mounted to a mooring line modem with the data being brought to the surface in real time. So I guess the question I've got is, we've got a whole range of sensors, far more than than most know from looking at our website. And the question, Greg, really is, with that, do you have what are the factors that users need to take into account when choosing monitoring equipment?
Huh. Oh. Oh, it looks like you're telling me the answer already. That's perfect. No, I mean, the first thing is to make sure you're measuring the right parameters. So obviously that's usually fairly simple. People who are measuring internal waves know that they need to measure temperature to do that. People who are measuring surface waves know they need to use pressure to do that. People who are measuring salinity or density know that they need a CTD. So making sure you're measuring the right parameters is critical. You do need to think about how long you want to measure for. Obviously, many of our instruments get used in both what I'm going to call profiling applications, where you're deploying for a short amount of time, maybe measured in minutes or hours, and you're moving the instrument through the water column. And generally, the data you're interested in is measured as a function of depth. But equally, there are a lot of people who are interested in leaving the instrument in one place in the water column and making a measurement that varies as a function of time. And generally, we call those moorings. So profiling and mooring applications can be quite different. And the kinds of variables that you're looking at and how fast they can change can be different as well. So those things are worth doing. Making sure that you don't buy a profiling instrument for a moored application, for instance. If you're going to stick something in seawater for years, you're going to have different concerns about corrosion than you are an instrument that only goes in the water for an hour or two every month. Sensor specs are important. And again, it depends on are you going to be leaving it in the water for a long period of time on its own, in which case drift is a critical parameter to make sure it's minimized? Or are you going to be able to redeploy this every few days, in which case a spot check that allows you to offset any drift means that a very drifty sensor that is might be problematic in a mooring application is perfectly well suited to a profiling application, because you're able to correct its drift every time you use it. There are some sensors that we have that you really should just spot check them every time you use them. There are others where, depending on the level of accuracy you need, you won't need to recalibrate them for a long time. Calibration costs and frequencies, yes, those are important. Maintenance as well. To be honest, the cost of maintaining our instruments is typically much smaller than the cost of getting to the site of maintaining them. So boat time, ship time, and labor time usually outstrip the cost of getting a calibration done, or the cost of cleaning the instrument with a toothbrush, or that kind of thing. So that tends to lead into making sure that when you select an instrument, you get the longest possible life before you have to go out to it. I mean, there's no point buying an instrument that's cheap if you have to go visit it every 3 days to change the battery, because you'll quickly offset that cheap purchase with expensive boat time and travel and on all that kind of thing. And those kinds of things come together to give you that $1 per data or $1 per day kind of figure. So those are things that we often think about, and I think most of our customers have as top of mind when they call us, and the kinds of questions that they're asking. Looking at the list of the people who are on, most of you, I think, have done lots of deployments yourself, and I suspect you have those same kind of concerns. So, yeah.
That's excellent. And in terms of comparison, how easy is it to compare apples with apples when comparing between different manufacturers and with similar sensors? Is that an apples for apples, or apples with pears sometimes?
So I think when you look at the data sheets of different manufacturers, you can find that they sometimes represent the key specifications in different ways. And so that can be challenging as a user to try and say, well, somebody says resolution over here and somebody says resolution over there, but do they mean the same thing by resolution or not? And very often, and we're guilty of this as well, the data sheet is intended to be shortened to the point rather than full of a lot of kind of metrological information that says how this was measured and how to repeat this test yourself. And so we say initial accuracy, but we don't spell out all the details of how to measure that initial accuracy yourself. It also can be challenging for a lot of users because they don't have the right equipment to do those assessments themselves. I've got to say, though, that in the last 10 years, the importance of accuracy and what I would call specification numbers has dropped off a lot, because there are 4 or 5 companies around the world that can achieve that, what I often call Mercedes-Benz level of specification, the top level. And those companies that have achieved it, the differences between them are not in how well you measure temperature or pressure or conductivity. They're how easy the instrument is to use and how reliable it is, and how quickly you get a response from technical support when you need it, and how fast a calibration can be done. And those are things that they're not in data sheets. And if they were, you probably shouldn't believe them anyways, because they come from your experience. And so what we find is that a tremendous number of our customers come back to us for subsequent deployments of subsequent instruments or proposals or projects, that kind of thing, because they've experienced it. It's not something that you necessarily, the data sheet is kind of what I'd call table stakes. You must be able to measure temperature to 2 millidegrees if you're going to be taken seriously in oceanography. And there are 5 or 6 companies, as I said, which can do that. But the big difference is, well, can you actually get their software to work? Does it work on the type of computer that you have? does it stay up to date, or does it look like it was written in the 1970s and upgraded for Windows 3.1 kind of thing? So comparison is sometimes about truly an apples to apples comparison. Sometimes it's about experience rather than comparison. And experience is comprised of so many different factors that are not numbers on a page. They're really intangible, and you need to try once, and then you will learn maybe whether your experience is good or not. And so often I think such a powerful way of learning that is to ask around. So you don't have to try every instrument in the world yourself. Ask your friends, ask your colleagues, what do they use? And we find that that's we find many people come to us who didn't know about RBR, but they come because they've asked their colleagues, or they've seen our equipment somewhere and asked the owner, how was this to use? And the answer they got is what leads them to ping us an email.
Yeah, no, absolutely. And I find from a sales point of view, people, you provide a lot of information when people first approach you, but once they've started using it, it's literally send me a quote and they do it there. It's a lot easier to for people once they've used it and got their hands on it. Absolutely. I was going to talk to you about a little bit about drift and resolution, but I'm wary of time. So I think what we'll do is I'll jump onto pressure sensors, and I have to mention, Eduardo, I can't see any questions or comments with the screen I've got set up. So by all means, interrupt if anybody has anything.
And I can see them as well, Steph. So we're okay at the moment.
Awesome. Okay, cool. Certainly here in Australia, a lot of our sales are around water level. So whether that's just pure depth, tide, wave, etc. And one of the common questions I get asked is, and we spell it out, and then people ask, we still have to clarify it. We have a range of sensors. So, with all of them, we'll have a standard depth offering of 20, 50, 100. You see it on the screen there, 200, 500, 1,000 meters with the standard logger, and far more with the logger. So do you want to explain to people why we have that different range of sensors?
Yeah, sure. I mean, so often when if we talk again about temperature, just as a really easy parameter to talk through, the specification of temperature is the same across the entire range of temperatures that you're interested in. So no matter whether you're measuring supersaturated salt water at -2 degrees, or you're somewhere lovely and tropical and you're measuring water at 35 degrees, our accuracy figure is exactly the same. It's 2 millidegrees. Pressure is not given as a value traditionally dbar. It's not quoted as a dbar value. It's quoted as a percentage value. It's a relative accuracy, if you like. And so for the instruments like the compact and standard range, the first 2 columns on this page, that accuracy figure is 0.05% of the full scale. And that's because the electronics really is tuned to the pressure range that you're using. So when you purchase the instrument, you specify the kind of deployment you're going to be doing. Now, it doesn't need to be super close. That is to say, if you are 20 meters of water, that's okay. You can use a 20 dbar sensor, and it doesn't really matter if it goes to 21 or 22 or 23 meters. Most of the sensors have between a 50% and 100% overpressure rating. That is to say, you can take the 2,000 meter sensor, for instance, to 3,000 meters of water, and before you start to physically damage it. Now, you can't do that with the 10,000 meter sensor. You can only take it to about 11,000, but fortunately, there isn't much water left at 11,000 meters, and so you can't drop it and let it go anywhere worse. So that accuracy figure, the 0.05%, is what is true for the more economical sensors that use piezoresistive cells. So that's the compact and standard instruments. The quartz-based sensors are a different beast. Instead of using the piezoresistive pressure gauge, they're using a quartz gauge, and that quartz gauge intrinsically has accuracy that's about 5 times better. Now, both of those figures need to be, you need to take into account whether, especially when you're looking at competitors' data sheets, they might give you an accuracy figure, but it's only for room temperature. And most oceanographic deployments are not at room temperature at all. So our figure is over the range of temperature. That is the case where an apples to apples versus apples to pears comparison can come up. So this, to sum up, the compact and standard have similar accuracies of 0.05% of full scale, according to the scale that you want to pick, and the quartz has about a 0.01% accuracy.
Okay, and that's great. And you talk about if you've got a 20 meter and you take it to 24 meters, you know, it's not going to pop, which is good. Do you have any comments on the accuracy? Because obviously it's calibrated over the whole range of that sensor, the 20 meters in that example. Yep. Do you have any thoughts on that?
Yeah, I mean, if you only go 10–20% above the nominal pressure range, the accuracy is going to be exactly the same. You can imagine it's kind of a smooth curve that fits some points. And if those points, if you measure outside of where the points are, the curve is still smooth. And so it's actually very close to its stated accuracy. It's only if you move a long way away from the last point we calibrated it at. I mean, maybe if you're at 50 to 100%, you certainly won't damage the sensors, but you may not get that accuracy. If you need that accuracy, we should really move you up to the next pressure range.
Right. Okay. And interesting enough, you talk about dbar. Why is things referenced in dbar as opposed to pure meters?
Yeah, I mean, it's one of the things that struck me when I first kind of joined the community, because the SI measure of pressure is the Pascal, but Pascals are way too small to be useful. But atmospheric pressure is about 100 kilopascals. In certain countries, you'll find that they do use pascals as a measure of approximate depth. And so 70 megapascals, for instance, means 7,000 meters. But the dbar is a great way of taking 1 atmosphere and dividing it by 10, so a decibar. And it's very convenient because it happens to be that in fresh water, a decibar of pressure is equivalent to a 1 meter addition of water. And it's not quite true in salt water because of the increased density, but to a first order approximation, it's like you can be bilingual. You can talk in pressure or depth. You can talk in dbar or meters, and you don't have to convert the number. So 20 dbar is the same as 20 meters to the level of approximation that's needed for specifying the pressure range.
Awesome. And then obviously being pressure-based sensors, we're measuring not just the water pressure, we're also measuring atmospheric pressure. So how's that accounted for within Ruskin and also in post-processing?
Yeah, so that's an interesting one, and that's kind of a philosophical decision that every instrumentation company has to make. So RBR has always taken the approach that pressure is measured relative to a complete vacuum. That is to say, if we say 0 dbar, we are measuring in outer space. If we say 10 dbar, and we're measuring relative to a vacuum, well, 10 dbar is 1 bar. That means that the instrument is just above the surface of the water because we're measuring the atmospheric pressure, which is 1 atmosphere. It might go up and down slightly as barometric conditions change, but that's true. Now, other companies often measure in what's known as sea pressure. And sea pressure is absolute pressure subtracting 1 bar or subtracting 10 decibars. And sometimes it can be confusing. If you take a data set from us and a data set from somebody else and you compare them, you'll notice there's a 10 dbar difference. And everybody starts to get in a little bit of a panic about it before they realize, oh, wait a minute, RBR is measuring absolute pressure, somebody else is measuring sea pressure. So it's trivial to convert between the two because it's just this delta of 10. And in Ruskin, if you want to see the depth of the sensor, there is already a sea pressure channel, which takes this into account. So that will give you the number in decibar. And when we calculate depth, we actually calculate its depth of water column. So we subtract 10 dbar or the hydrostatic pressure, whatever you've set it to. We subtract the atmospheric pressure, and then we convert that to depth. And the conversion from pressure to depth, obviously, it's much more precise to use the density of the water rather than just saying it's 1-to-1 dbars to meters. And so in Ruskin, you can put in the density of water so that the depth correction is calculated correctly. Or you can also use the UNESCO TechNote 44 technique, which involves it basically allows you to plug in the latitude of where your measurement was, and it gives you an approximate density of the seawater and uses that. So that is one difference, that some companies have traditionally talked about pressure relative to the sea surface, and others talk about pressure relative to absolute zero. We generally work at absolute zero and then just do all the conversions from there.
Okay, great. Did you take a logger? I see you're at home. Did you take a logger home?
Unfortunately, I usually, being the sad kind of person that I am, do have loggers around, but I don't have any with me. You've got some on your shelf behind you, I see.
Yes. So, okay. So,
I said earlier.
yes, yes. Well, I didn't, because I had the cap off it still. So, I just thought we would run through the inside, and maybe I should stop sharing the screen, and then you get to see a fair.
Or I can pin your video instead. You don't need to stop sharing, but yeah.
Oh, okay.
So we can talk a bit about the anatomy of the logger. It's kind of interesting even to know the vocabulary that we use. If you hold it a little bit to your right, so we can see the whole thing top to bottom. There we go, perfect. So we've got two red things. In Steph's right hand, he has what we call the battery end cap.
Greg, could you actually pin his video? When you speak, it goes to your video.
Right. Yep. Sure, I can. Better?
No, maybe we have to pin it. Maybe that's just for you.
Hold on. I think I need to spotlight him.
There we go.
There we go.
Thanks.
Pinning or spotlighting sounds like a voodoo doll to me. So he's got an instrument in his hand. It's got two red ends on it. The end on his right hand that he's clutching is the battery end cap, so-called because it's an end cap, and it's where the batteries are. And this is the only end that a user ever needs to open. You don't need any tools to open any RBR instruments. You just twist the end cap open. And so if he undoes that end cap, a couple of things happen. First of all, the O-ring is unseated. You can see that black joint there. And while he's unseated the O-ring, the thread is still engaged. And this is a safety mechanism that not many companies have actually designed in. If this instrument ever had a leak at depth and came back to the surface fast, it would effectively be a bomb, because although water doesn't compress very much, it does compress enough that you've stored some energy and it's inside. And so when you open this, if that thread disengaged, you'd get a bit of a shock, because the red end would end up being a projectile and shooting across the room. So RBR instruments always release the O-ring first before the thread, so that the water that comes out basically makes a rather surprising spray, but you don't end up with 100 or 200 grams of plastic or metal shooting across the room. All right, so he carries on then and takes the whole end cap off, and it just comes off neatly in his hand. And inside the end cap is the desiccant. So you can't see very clearly on the video, but that is silica-based desiccant. It's color indicating, which means that when it's one color, it's wet, and when it's another color, it's dry. It usually starts off life dry and then becomes wet. A little factoid for everybody: having desiccant out in the open air uses about 50% of its capacity in half an hour. So you don't ever want to have that end cap just sitting around on your desk before a deployment, because you've used up most of that desiccant's capacity to absorb the moisture that was in your room or your cabin or wherever you are prior to dropping the water into, dropping the instrument into colder water where it might condense. The other thing that you can just see glistening there on the outer part at the kind of 11 o'clock position on his video is the core of the twist activation. So all standard RBR instruments can be started or stopped without a computer simply by twisting the end cap about 45 degrees. And you'll see on the housing, there's this little label that says pause and play. And if you hold up the end cap at the same time, we'll see a little icon that's on the side of the end cap, a little square usually, a little bit higher. Yep, there's the square underneath the Wi-Fi symbol. And so when you close up the instrument, you'd notice that that square is going to be aligned with the run side or the play icon when it's fully inserted. Oh, now I'm going to make him undo it in another second. He's going to turn into a muscle man, but carry on going. And
Okay.
yeah, so when it's fully closed, it's aligned with play and the instrument will start logging. There we go. And if he backs it off about 45 degrees, then the instrument will be in the paused state. And what's helpful about that, because labels, of course, after years of use get rubbed off and what have you, is that the instrument vibrates in your hand. So you know when it's running because it's vibrated. And it actually vibrates two different codes, two different, let's call them ringtones, one to start and the other to stop. So when we look inside the other end and rotate it over slightly, that's it, we can see two connectors. If we rotate it 180 degrees, Steph, just there you go. So we can see the two connectors down below. The one on the right is USB-C, and that's the one that you typically plug your laptop into, just above the pencil. And then the one on the left is a special connector that's used for underwater connectors going to the battery end cap. So we have versions of the battery end cap that have a connector on them, and they need a little umbilical on the inside, a little spiral cord that goes from the end cap itself into the logger, and it goes in through that connector. Up above, you can see the battery curtain, which has two plus indicators in it, because that's going to be the polarity of the batteries you put in, and a little arrow indicating in and down. And so if Steph, even without being able to see it, pushes in and down, he can get that battery cap open. There are those two positive terminals of the AA batteries. And in a standard logger, there are 4 on each side, so 8 in total. At the other end of the instrument is the sensor end cap. And the sensor end cap on this instrument is a little harder to see, especially on video, because the white is difficult to differentiate from the housing. But Steph can put his finger on the line in between the housing and the sensor end cap. So actually, can you just wrap your hand around the logger right where the join is between? So he's holding onto the sensor end cap there. If he slides his hand down a little bit, and stops, in fact, you can almost see the black of an O-ring through the white of the plastic there. And so there's an interface there between the sensor end cap and the other end. And you don't ever need to open the sensor end cap on an RBR instrument unless it's very special instructions from support. The electronics are inside there, and the idea is to keep them away from grubby fingers. Sensor end cap is so called because we've got all the sensors on it. So this one is CNT, and the pressure is in underneath that little clear cap. And then this instrument also has the so-called Sputnik end cap, which allows us to mount two cabled sensors. Sanish, it's good to see that you remember the training we did on this in 2013. It was indeed a long time ago, but yeah, I probably wasn't far ahead of you when I was doing the training back then. So yeah, that's the overall geometry of the kind of outside of the logger. I don't know whether there's anything particular else that I should cover there, Steph?
No, I think it would be good to talk about the batteries. Because it's a question that always comes up.
Yeah, absolutely.
If I can.
Yeah, you're not on the. I'm seeing your presentation view rather than your full slide.
Ah, okay.
Like I think maybe it shared the wrong screen.
Yeah.
But yes, one of the things that's happened with, well, the two main things that happen in our third generation of instruments were that we changed from an older connector to USB-C, and we changed from an older type of battery to AA batteries. But of course, AA batteries come in variety, not of shapes and sizes, but of chemistries. And each of those chemistries has a different amount of energy stored inside it that's available to use. Now, the first thing that we've always wanted to do in terms of batteries at RBR, and indeed connectors and cables, is to ensure that customers were never held hostage to us because they needed to come back to us for custom batteries or custom cables. So, you know, there's this nice table here that shows that it is possible to build an instrument that's got batteries in it that are only ever going to be used once. But I think this is a terrible idea because we have enough batteries in landfills already without the idea of having to put deployment batteries and their instruments into landfill. If you have to send the instrument back to the manufacturer to change the battery, well, it's quite expensive and it's a lot of time. But to be honest, most people have the choice between proprietary batteries or off the shelf. And RBR has always taken the off the shelf approach and said that you should be able to get those batteries locally, cheaply, and without needing to go through RBR in any way to get that done. But there are still companies who insist on making proprietary kind of shrink wrap battery packs, and you have to buy them from the manufacturer. And that's a bit, I feel that's a bit like the kind of Gillette model of razors, that you sell the instrument cheap and then you make a stupid amount of money by selling batteries at an overinflated price. And it's just something that RBR has always tried to avoid doing. The negative, of course, of the power to procure your own batteries is that there are a variety of quality options out there. The positive is that once you found a good one that you can source locally, that's great. Now, we also support a variety of AA battery chemistries. Of course, we all think of alkaline batteries, and maybe depending on your region of the world, those might be famously as Energizer or Duracell or Rayovac or Philips or what have you. And alkalines are pretty good, but they do lose a lot of their power in low temperatures. However, there are a variety of other chemistries available in the AA form factor. And so alkaline batteries are the chemical name for it is it's the third one down here. It's the zinc manganese oxide ones. And these are actually in this list, these are arranged in order of capacity. So alkaline batteries only have about 30% of the capacity of the very best option that's available for AA, and that's the first one, lithium thionyl chloride, or LTC. The chemical name is SiSoCl2. So if you treat that as the gold standard at about 100% capacity, then the next one down, lithium ion, is quite good. They're usually marketed as Energizer Ultimates, for instance. They're about 50% of the LTC batteries. Then alkalines are about 30%. There are two rechargeable batteries available, lithium ion, though they're not very popular, and they sometimes come with slightly disturbing trade names like Ultrafire, which doesn't bode well for how satisfactory they're going to be. And then nickel metal hydride. And nickel metal hydride are a chemistry that's been around for quite some time. Very reliable, super cheap, and easy to obtain, and easy to charge overnight. So although the capacity is very low, it's only about 25% of the lithium thionyl chlorides, but if you only need the instrument to profile during the day, and you want to profile again with it tomorrow and the day after and the day after, then absolutely use a rechargeable battery. You don't need to have guaranteed long autonomy. You want to avoid as many batteries ending up in the rubbish tip as possible. So yeah, that kind of I think that covers
absolutely. And I think the one of the other things to mention is that within Ruskin, we have a fresh battery tick, so that you when you put your new batteries in, the logger remembers when you've done that, the number of samples is taken so that you maximize the use of that battery. But then again, going back to one of the original points that you mentioned, Greg, we have to make sure we weigh up the cost of the battery as opposed to losing the data if the battery has failed, because as we all know, battery chemistry is very very complicated, and shelf life and temperature and all sorts of things come into it.
Yeah, absolutely. Okay.
Okay, so, say that again.
What should we think about next?
I'm thinking about mounting the loggers, just some sort of ideas. You know, we've talked about the insides of it, but some ideas about things we should take into account for our deployment. So, you know, protecting it from biofouling, for example. I see there's a question about biofouling, orientation clamps, and that sort of thing.
Okay. Well, first of all, instruments get held onto things with all manner of contraptions, and clamps are definitely the most reliable way of doing it for the long term. But people use tape, zip ties, bits of string, and depending on the deployment scenario, those may be absolutely sufficient. I wouldn't generally trust a bit of string, but some Dyneema or Spectra, which is usually, even at a couple of millimeters, rated to hundreds of kilograms of load, is absolutely fine. In terms of protective mechanisms, some people also take our beautiful loggers that we spend a huge amount of time shipping clean and with beautiful labels, and they wrap them up in tape. One of the main reasons for doing that is that the instruments get dirty when they're underwater. And so when you recover them, all you have to do is slice down the side and kind of peel off that jacket of tape that you've put on, and you've got an instrument that looks pristine again, and saves you a lot of time kind of scrubbing and cleaning and that kind of thing. Pressure sensors, in particular in kind of high sediment areas, can get filled with sand or grit or other kinds of sediment. And so one of the things that you'll notice on the RBR pressure sensors is that they come with a little cover, and that cover can be opened with a coin. It'll work very well with a Canadian $1 coin, but most countries in the world have a coin that's suitable. If you really can't find a coin, and to be honest, coins are kind of on the way out, then you can put a screwdriver in there as well. Doesn't require much pressure. And that cover has 4 small holes in it. Those are the only place that need to be clear for the pressure to get through to the sensor. And so if you want, you could put, for instance, what in North America we call geotextile membrane. That is to say, a piece of fabric with much, much smaller holes in it. And you could tape that over the cover. It will still allow water pressure through, absolutely fine, but it will stop sand building up inside. So a lot of people will do that if they're in particular situations. You know, that photograph in the bottom left is in Lake Tahoe. It's amazing. You're in like 2 or 3 meters of water, and you can see the bottom, and you can see the shadow of the boat there. Less concerns there than there are in other places. Most of these pictures have clamps, although that one from Vietnam in the middle center, that's a load of zip ties and duct tape. And it's a bit, as the English would say, Heath Robinson, as the Americans would say, Rube Goldberg. It's a bit improvised, but it gets the job done. And yeah, there is one perhaps important consideration to talk about for the conductivity cell. So you can see that top left photo, actually second from the left. There's kind of a logger that's been laid down on somebody's towel or a cloth. It's got 2 blue clamps on it and a piece of mooring line there. So the proximity effect here is that our inductive conductivity cell causes some electric current, very, very small level, to be put into the water. And it travels through the water and approximately goes out about as far as 15 centimeters or 6 inches from the center of the instrument. 80% of that measurement is taken inside the cell, and only 20% is out in that 15 centimeter area. But we calibrate the instrument in open water, effectively. So when you put it next to a mooring line, that current that's in the water gets modified. If that mooring line is a conductor, then all of a sudden logger sees a conductivity that's slightly higher than the salt water. If the mooring line happened to be jacketed, and it's therefore an insulator, the conductivity cell sees a conductivity that's slightly lower. Now, how big is that difference? Because while this is a true phenomena, the question is, does it actually matter? So on that left-hand clamp, which is 7.5 centimeters, remember we just said that the field goes out about 15 centimeters on either side. But we're saying here, we're only half of that distance. That's the short clamp. And what we're seeing there is, so this table shows a ridiculous number of digits, which is not necessary. It's the 0.0025. In fact, I'm just going to leave it at 0.002, or we can round it to 0.003. So if you were to clamp it with no consideration at all, you will get about a 3 milli-PSU delta from the calibrated value. And that's additive. That means that you can just add that number no matter where you are in your salinity measurement. Now, if you use this long clamp that we have available but don't use very often, you effectively won't be able to measure the difference at all. That's 0.05 milli or 50 micro PSU, which is about equivalent to 0. That is to say, even a good salinometer will have trouble seeing that difference. So proximity effect sometimes is a little over played up. And for most people, especially in coastal situations, to be better than 3 milli-PSU is excellent already. What else have we got on this? Any other slides there?
I just thought I would also mention now, Greg, when we're talking about the sensors and mounting that, is that we put a lot of thought into the orientation of the clamps and sensors, etc., either on a multi-parameter CTD or where we put it on longer cables here for the wire walker. Do you want to talk through these?
Yeah, I mean, I think that particularly the key ones to talk about are the optical ones, because they do have a sensitivity to sunlight. And so when you bring the instrument, as in the case of a wire walker, right up to the surface, and sometimes the instrument might come out of the water and see the air, see the sun with no water protection at all, instruments that are measuring oxygen or fluorometry or backscatter and are receiving light in to measure some other parameter, they can be deceived by sunlight. And so typically we don't aim those up, we aim those horizontally. And so on this wire walker deployment, you can see that the optical fluorometer, the dissolved oxygen, and the transmissometer are all left down in the water and aimed horizontally. The only optical sensor that's looking up is PAR, and that's because it's intended to measure the strength of the sunlight. And so that's absolutely fine. Now, we also, on profiling instruments, take some care to make sure that the sensors measure as clean a body of water as possible before it's been contaminated by the heat of the instrument. So we always try to move the sensors through the water, and the body of the instrument is behind them. From that description, you can tell that this wire walker is intended to make its best measurements going upwards, because we put the CTD facing up. The same is true when you look at an Argo float. The CTD is facing up, and it actually makes its smoothest profile when it starts at 2000 dbar down and comes to the surface. The measurement it makes when it's going in the opposite direction is pretty rubbish, because all the metal of the Argo float contaminates the temperature and the conductivity results. So while you might profile an instrument on a line from a ship with the CTD facing down, on some of these vehicles, you face them up instead. So you need to be aware of that.
Cool. I've got a question here from Alan Kemp, actually, and one of Alan's favorite tips, by the way, is with the pressure sensors, is he puts nappy cream, diaper cream with the zinc on the top, because it still allows the pressure to move, but it reduces some of the growth in there.
Yeah.
Candice didn't think I could get you to say diaper cream on the video, but anyway, I had to put it in there. So Alan's asked, would you consider a locking pin or mark the sensor end of a logger with twist activation as well as the battery end cap? The reason he asked this is I've seen how people have used sensor end, especially with a cage, as a grip to undo the battery end cap. And this has caused the sensor end cap to unintentionally twist loose slightly and moves the pause and run position of the battery end cap. And mostly means you have to tighten the end cap tighter and tighter until it doesn't work anymore.
Yeah, no, that's true. So that's a good point. What we have tried to do on many of the sensor end caps is to make them as small as possible so that they're very difficult for you to think of grabbing. When you hold the instrument up in front of yourself, you go, oh, there's a big red thing to twist, and oh, there's nothing really at the other end, so I'll just hold the housing. And that's intentional, so that one hand is on the housing, the other hand's on the battery end cap. Once you put it in a cage, yes, all bets are off. And if that clamp is to the sensor end cap, then I can see that rotating it especially would cause a problem. So it's a good idea, Alan. We'll see whether in a revised design, there's a way of really fixing it so that there is no way to unintentionally get it undone. The thing to say though, although it does change the position of twist and of pause and run, you do have to rotate the end cap by probably 2 full turns before the O-ring is exposed. And so although it's irritating, you don't have the risk of causing a leak by doing that unless you're really, really going to town and do 2 full rotations and don't realize what you've done.
Okay, great. I was going to go through a few things, but with sort of time's flying on. So I was just going to get you to mention a couple of things about biofouling and ways of preventing that. We've talked about tape on the outside. We've talked about nappy rash cream. And there's also wipers. We've got some instances where wipers would be useful.
Yeah, so this picture on the left is actually the oxygen sensor in a deeper part of Lake Tahoe. And what you can't really see is that hidden under all that filamentous algae is a toothbrush wiper. And it looks, at the beginning, before you deploy it, it looks very similar to that picture on the upper right. So these are wipers made by Zebrotech in New Zealand. And they are, I'm sure they wouldn't like them to be called glorified toothbrushes, but that's what they really are, is a glorified electric toothbrush. It just doesn't vibrate, it only moves once every couple of hours or half a day. And so those are quite useful for wiping surfaces that can be wiped. Not every surface can. For instance, in dissolved oxygen, you can wipe the slow optode, which has a black Teflon membrane on it. You can see that kind of black spot, like Cyclops in this photograph. But you cannot wipe the fast optode, which has a pink spot, because that pink spot is actually the sensing element, and it's fast because it's exposed to the water, but it's also vulnerable. If you use a brush on it, you'll wipe it off. So hopefully that gives you a little bit there. We're continually looking at some anti-fouling options, and I expect that in the next few months, there will be an announcement from us about the availability of an excellent anti-fouling option for our CTD. It will require external power to have enough juice to run for long deployment. But if you've got solar powered buoys or you've got a cabled observatory, that'll be an excellent solution.
Excellent.
Dinesh, that might have actually answered your question at the beginning.
You're right, Greg. I think that's right. It answers the question because there is a program which is going on at this point in time for the tender. Maybe I'll take it up with you privately, but
okay.
If this is coming up in few months, maybe we still are good.
Okay.
Because, but for the biofouling, we are looking at, because if there is a provision for an intervention every month to go down to the locations where the buoys are placed. So anyway, I think maybe I will definitely write to you. Then we will see where we can.
Dinesh, I have my apologies. I did see that you wrote to me recently, but I've been on holiday. The best thing to do if you have a question is to write to info@RBR, because even if one of us is away, somebody else will be able to deal with it promptly.
Oh, there's another question. There's another question there from Anoop.
Oh yes, Anoop. Yes, I see this about the Cervelo. That's an interesting idea. Yes, a Cervelo light. So that would be worth Anoop writing and talk to Eduardo a little bit about that. We'd be interested in knowing kind of what the market is for that. It has been a while since we made the TGR 1050 HTs. Steph, I think, still has one in Hobart that's probably out of the water now, but was deployed at watching the Australian tides for many years. All kinds of things are possible. So, but they're really driven by how popular you think it would be. So, if you could write a bit more about that idea in an email, that would be excellent. I'd be happy to talk about that more with you.
Absolutely. Desiccant, you've mentioned it earlier. I think it's worth mentioning, Greg, that this is the original ones we had, where you can see nice and blue, and mine are down here somewhere because the cap's been left on my desk while talking, but I've got spares if we ever deploy it. But so also the
thing to say is that on that color scheme, those desiccants that we used to use are made with a little bit of cobalt inside them, and that's what gives them that beautiful blue color. But cobalt is something that we're trying to get away from. And so you may find instruments now that instead of having desiccant that comes fresh as blue, it comes fresh looking orange. And the balls inside are much bigger. Rather than being crystals, they're really almost tiny little ball bearings. The nice thing about this one is, one, it has no cobalt, so it's better for the environment when it eventually does get discarded. But secondly, it's completely reusable. And we've injection molded a canister. You can just see it here. It's got a lid on the top, and you snap that lid off, and you can empty the silica into a plate and stick it in the microwave. And you will convert it from its wet color of being that kind of dark greeny blue back to orange relatively quickly. You can also dry it in an oven or a food what do they call them here? Desiccator. But any technique you like. However, don't ever do it inside the plastic capsule, because the plastic will distort, and then you won't be able to fit it in the housing properly. So that's why they've got caps on them. It's so you can take it out and redo that. And again, once you've got the desiccant, don't come back to us. You can get desiccant from anywhere you like and reuse it in those capsules.
And I think just finishing off, just some useful information in terms of for people using it is O-rings and how often they should change their O-rings and how much of the grease should we put on it, because I see lots of people send their loggers back and it's caked in it.
Yeah, more is not better when it comes to O-ring grease. So the rule of thumb that we use is we put a little spot of grease on our fingers or fingertips, and then we pick up the O-ring and we kind of rub it between our fingers, as you see here. And if in the case, so in this photograph, it's actually quite nicely illustrated. You see how the O-ring held between the chap's thumbs is shiny? That means it's greased, and that is all the grease it needs. If it's not shiny, it needs more. If it's shiny, stop. You should never be able to see a blob of grease. So O-rings really don't need a lot. They just need enough to be able to move into position. And the trouble is that if you put more on, you may jeopardize the ability of the O-ring to move to the right position under pressure and actually cause a leak. In addition, O-ring grease, just like any kind of grease, it attracts dirt and it sticks to it. So you want to have as little as possible so that as little dirt collects on it. When do you change them? I would say that an O-ring that is not opened, that is like the ones on the sensor end cap or the ones that we have inside the conductivity cell, you don't ever need to worry about it. The only end caps, the only O-rings rather, that you need to change are the ones that you expose regularly and have the potential for either being damaged by being cut, like on that battery end cap, or the potential for collecting dirt or hair or dust or whatever it is. Now, the way that the photograph is holding this O-ring is actually very similar to how those of you who ride a bicycle might be used to squeezing the inner tube back onto the tire. That is to say, we do send an O-ring tool with every instrument, and it's made out of plastic. And the reason we do that is because some users think they need a tool and they grab a metallic tool. And metallic tools are bad, not because they damage the O-ring, it's because they damage the O-ring groove. And that's really difficult to repair. So instead, you actually grab the O-ring on both sides and you kind of squish and push all the excess up to one end, and then you can just lift it off. Try it and you'll find out it's easy. If you are not very dexterous, then use the O-ring tool. Now, I think Alan jumped in saying, should we do this on the backup ring as well? Is that right? Yep. Yeah, he says, does the backup ring also need to be greased in the same way as the normal O-ring? Yes, it does. So both of them need to slide slightly. You'll notice that when they're in position, the groove is just a fraction bigger than the O-rings. And when you close up the instrument, the O-rings are typically get pushed to one end of that gland by the action of closing it. And typically the way the instruments are designed, when you apply pressure, those O-rings need to get to the other end of the gland. And the main function of that grease is to help the O-ring migrate the millimeter or two without getting snagged or twisted or caught up. You can see in this picture that on our compact logger series, we always use a standard O-ring, which is circular in cross-section, and a backup ring, which is square in cross-section. Now on the compact logger family, the backup O-ring is always there, even though they might work at low pressures. On the standard logger family, we only put the backup ring in when we have titanium housings, because it's only really needed for high pressures. It's just on the compact logger family, it's very easy. It's just easier to make them all the same. So it's important though, that the backup ring, if you take it off, that you remember which side of the normal O-ring it goes on. It always goes on the low pressure side. So you think about this instrument being closed, it's going to be atmospheric pressure inside on the left, it's going to be higher water pressure on the right. So you want the O-shaped O-ring on the outside, and you want the backup ring on the inside. Because if the backup ring is on the other side, it provides no support at all for the O-ring. I won't get into those pictures, but they do illustrate how the backup rings work. Unfortunately, they show a kind of double backup ring, which is a bit confusing. We don't use double backup rings, but there we go. I know we're out of time. Ben, you are asking, are we considering doing a coda wave? So yes, you can you do need to currently process to do wave statistics off the coda. The coda is a fairly simple and straightforward instrument that will stream pressure bursts to you. We look occasionally at whether it's worth the kind of computational power required to do that analysis in situ, but it's generally, there are relatively few people who need it and who want it to be done in situ and who aren't capable to do it themselves.
Okay.
Stanish, I see that last question from you. The battle cards, yes, I think Eduardo has been working on them. He may not be able to comment now, but I'm sure on the next agent meeting, he'll be able to deal with that question and talk about when those are being rolled out.
Yes, that's right. Actually, both Steph and I have been working on those.
Oh, perfect.
Yeah.
So I'm sure that probably wraps us up for time, doesn't it, Steph?
Yeah, absolutely. Just one very last question, because it comes up frequently, is cleaning the sensors so we're ready for deployment again. Yeah. A lot of people ask about vinegar, whether we can use pure vinegar, a vinegar solution to soften the calcium growth.
Yep. So absolutely, any kind of vinegar is fine. I wouldn't use a harsher acid than that. And I wouldn't expect that the vinegar necessarily works instantaneously. So on a pressure sensor, for instance, you never want to touch that membrane, but you might get some kind of buildup on it. And so to loosen it, I would invert the instrument and stick it in a cup of vinegar overnight, give it 12 hours to soak, and then you'll find it just falls away. I wouldn't use a harsher acid because there is actually quite a few different materials there, not just the plastics, but the O-ring particularly, you don't want to start having the vinegar or the acid start trying to eat away at the O-ring grease that you so carefully put on the right amount of.
Absolutely. And don't do it just before going into lockdown and you can't get to your office for a week because your logger
Smells like fish.
doesn't like that. Awesome. Okay, well, great. Thank you, Greg. Look, we're always open to carrying on these discussions outside these forums. Hopefully you found it useful, and thank you for taking part, and thank you, Greg, for being the key. It was interesting. I had 80 slides prepared because I didn't know which direction your answers were going to go, so I've managed to flick in between them reasonably well. So that's good. So thanks for that. But please don't hesitate to contact us. My email was at the beginning. I won't share the screen again, but it's steph.stimson@rbr-global.com, and the info@rbr-global.com is the main one, and I have access to that as well. So please don't hesitate to get in contact with us. And we're going to have a little break in this series now to do some catch up, but we're going to hopefully have a new series coming later on in the North American fall and our spring summer. So we'll keep you posted with that. So thanks very much, and enjoy the rest of your day, and have a good evening to those in North America.
Okay, good night, folks.